Hello and welcome to my Physics Lab 4 presentation. In this lab, we examined the motion of a spring mass system from a video in which the mass swings in an arc while oscillating on the spring. We aimed to analyze the object's motion and its energy changes and simulate that in a computational model. This lab is significant as the motion it represents is similar to that of extreme road sports, and we were able to see the energy principle in action. At the end of the lab, the graphs created from the computational model suggested similar behaviors in regards to motion and energy to the observational model obtained from the video. We used the video given to analyze the motion of the spring mass system in Tracker. Position points were taken as seen by the red diamonds. Doing so, I obtained the mass's initial position. Since the mass was dropped from rest, we also assumed it had an initial velocity of 0 meters per second. Mass and length were given from lab instructions and the model video from edX. The approximate period of oscillation of the spring mass system was calculated by taking the average of 2 periods of oscillations from the graph made by plotting the position points, which gave us a period of about 1.619 seconds. Using the formula for period, we also derived a formula to find the spring constant, which turned out to be around 6.0547. This was the given video. Before we get to the computational model, let's first review the fundamental principles needed. Formulas for gravitational and spring force are needed because they make up the net force on the system. We will also be using the energy principle for this lab. Since our system includes both the Earth, spring, and mass, by the energy principle, the change in energy at any time should be equal to 0, as no external forces are acting on our system. Additionally, we need the formulas for kinetic energy, gravitational potential energy, and spring potential energy, as they all apply to our system. In GlowScript, I plugged in all the values for the known variables, based on given information and initial observations as shown in previous slides. The relaxed length of the spring was found using fundamental principles. At equilibrium, the magnitudes of gravitational force and spring force have the same value. Thus, we can set them equal to each other and modify them to find the value for the relaxed length, which I solved to be about 0.04933 meters. We plugged in the constants and variables used in each force formula. We need the two forces acting on our system to solve for net force, which is needed to calculate both velocity and position of mass at a given time. Velocity and position are needed to obtain not only the motion of the mass, but also to calculate energy changes throughout a period of time. All of our previous calculations are then put into action in applying the energy principle. The delta variables are used to calculate changes in energy over a relatively small period of time, which we determined to be around 1/210. We will be extracting the position points from Tracker to simulate the mass's behavior. This was the final product. As you can see, the simulation is similar to that of the video. The following X and Y position time graphs were obtained from the computational model. As you can see, the model positions were relatively similar to the experiment or observational positions used. However, the Y position time graph does have more discrepancy between the model and experimental data. This graph shows the total energy changes and the individual energy changes over time. As we can see, the total energy change is constant at 0, which means that it satisfies the energy principle. Since our system included the Earth, mass, and the spring, we stated before that the total energy change should stay at 0, since no external forces would be acting on it, so any transfer of energy is internal. The computational model then follows the energy principle. Going back to the tracker data, if we compare the oscillation periods in the X and Y direction, we can see that they are similar but definitely not equal. The estimated periods in both directions were calculated by taking two oscillations from the data and averaging them out. The discrepancies between each oscillation periods could be due to human error while measuring the position of the mass, but it is most likely due to the fact that there's a greater net force in the x direction while the y components of both the spring and gravitational force are working against each other. Thank you.